Hello everybody, this is Dr. Christopher White and welcome back for part 2 of Cenozoic Earth history, focusing on the Paleogene and Neogene. So now we're going to move on to North America's western margin. So we're going to move on to the North American Cordillera. Now, the Cordilleran Belt consists of a complex mountainous region. It stretches from Alaska all the way down to central Mexico, and it has a maximum width of about 1,500 kilometers. Now, the mountain range itself isn't one mountain range. It's actually several distinct mountain ranges combined together to form the Cordilleran mobile belt. Now, we have a nasty habit of referring to this belt as the Rockies, but in reality the Rockies are only one of the sets of mountains that actually makes up the belt as a whole. Now, in terms of the geological history of the western margin of North America, it's gone through periods of being a passive margin and an active margin, and as we know, it's mostly been an active margin from the Mesozoic and into the early Cenozoic. So, just to briefly review the geological history of the western margin of North America, so we know in the Neoproterozoics, that's the late Precambrian, the margin was passive. So it was essentially a nice, stable, boring marine environment. Now, as we move into the Paleozoic, this passive margin continues, although there is a short event in the Devonian, which is the antler orogeny, during which a portion of the western margin becomes active. So we do get a limited period of subduction, but the antler orogeny in the grand scale of things is actually quite small. Now, as we transition from the Paleozoic to the Mesozoic, so that's the Permian-Triassic boundary, we have the onset of the Sonoma orogeny. But once the Sonoma orogeny is complete, we then return to a period of being a passive continental margin. And this period of being a passive continental margin essentially extends from the Middle Triassic to approximately the Middle Jurassic. Now, as we enter the late Jurassic to early Cretaceous, we have the onset of a sustained period of being an active continental margin. So this is going to lead to the formation of the Cordilleran mobile belt. Now, we know the formation of the belt consisted of 3 distinct orogenies: the Nevadian, the Seaver, and the Laramide orogenies. Now, by the early Paleogene, so that's the Eocene, the Laramide orogeny has completed itself, and we have since moved into a period of being, on the whole, more geologically quiet, although subduction does still continue in the Cascadia zone, and the Cascadia zone essentially stretches along the western coast of North America between northern California, through Oregon, through Washington state, and then into southern British Columbia in Canada. Okay, so let's move on to the Laramide orogeny. So we know the Laramide orogeny is the final orogeny of the 3 orogenies that formed the larger Cordilleran mobile belt. Now, the Laramide orogeny began in the late Cretaceous, so we already discussed it a little bit from the previous Earth history lecture. However, it continues going until the Middle Paleogene, to be more accurate, the Eocene. Now, the orogeny was not focused in a region proximal to the trench, and this differs significantly from the Nevadian and the Seaver orogeny. So the Nevadian and the Seaver orogenies were essentially focused more towards the trench itself, so more towards the subduction zone. And this is because a lot of the pressure, a lot of the force from the subduction event was being focused at the contact between the 2 pieces of crust, essentially the oceanic crust of the Farallon plate and the continental crust of the North American plate. And because they were pushing against each other right at the point of the subduction zone, that meant most of the pressure was located quite close to the trench. And so we tend to find the Nevadian orogeny especially has most of its deformation very close to the trench. We know the Seaver orogeny, most of the deformation was slightly more to the east, and by the time we move into the Laramide orogeny, we can see that the deformation has moved even further east, so it's gone even further inland. Now, we've already touched on the fact that this change in the position of the deformation is the result of a change in the angle of subduction of the Farallon plate underneath the North American plate. So, unlike the Nevadian and the Seaver orogenies, which mostly consisted of quite strong compressional tectonics, which resulted in quite tight folding and lots of thrusting, The Laramidogene actually produces a different style of deformation. So with the Laramidogene, we see quite a lot of vertically uplifted fault-bound blocks. So we get these big blocks of rocks being pushed up on using steep reverse faults. Now, most of these steep reverse faults are probably actually pre-existing normal faults that have just been reactivated. So the fault is already there, and so all tectonism has to do is just simply use it again, because it's the easiest way of doing things. Now, once again, the Neogene and the Subductions were associated with volcanism. The Laramidogene is not. So we don't really see much in the way of volcanic activity during the Laramidogene. We also see that in terms of deformation, we lose the tight folding that we get with the Neogene and Subductions, and instead the folding we get with the Laramidogene is more open, gentle, so you get these quite broad folds. And of course, as we've already touched on, the region which is being deformed as part of the Laramidogene has moved even further to the east. So essentially, we've been progressing from the Neogene, which was located quite close to the modern-day west coast of North America. Then as we step east, we then had the Subduction, and then as we move even further east, we then move into the terrain which is being deformed by the Laramidogene. So to account for this eastward shift, we have to make adjustments to the subduction model for the mountain belt. So during the Neogene and the Subductions, the angle of subduction of the Farallon plate is somewhere between about 50 and 20 degrees. So we know subduction initially started off being quite steep during the Neogene, and then as we move from the Neogene into the Subductions, we begin to see the angle of subduction shallowing. So the subduction produced plutonism and volcanism between 150 and 200 kilometers inland. So if you remember, the subducting oceanic crust will go down into the mantle until it reaches a depth of approximately 150 kilometers. This is the point where the mantle the oceanic crust, will dewater. That water goes into the overlying mantle, and essentially it melts it through hydration melting. So the mantle melts, producing a mafic magma. That mafic magma rises straight up, gets stuck at the base of the continental crust. It partially melts the continental crust, producing felsic and intermediate magmas, and those felsic and intermediate magmas rise through the continental crust and essentially are erupted onto the surface via volcanoes. Now, the vast majority of this volcanic activity is 150 to 200 kilometers inland from the trench, which is running parallel to the west coast of North America. And so this tells us that essentially the subducting oceanic crust was making it down to that magic 150 kilometer depth, approximately 150 to 200 kilometers east of what is now the modern day west coast of North America. So combined with this volcanism, we see a lot of essentially compressional tectonics resulting in tight folding and lots of thrust faults. And so this is what we expect to see in a normal convergent plate boundary. Now, by the late Cretaceous to early Paleogene, it's thought that the angle of subduction had shallowed to nearly horizontal. And so this means that instead of diving down into the mantle, the subducting piece of Farallon plate is actually just grinding along the bottom of the North American plate. So, of course, number one, this means the subducting Farallon plate is never going to make it down to that magic 150 kilometer depth, and so you don't get any melting, so obviously you're not producing magma, so that means no volcanoes. It also means that the area which is being deformed by the interaction between these two pieces of crust is now considerably larger, because rather than all the pressure being focused towards the subduction zone, it's now spread out along the entire bottom of the western side of the North American plate. So this means that the tectonic forces are a bit more dispersed, so we lose the very, very tight folding, and we lose the thrust faulting that we've seen with the Neogene and the Subductions, and it's replaced with very broad open folds, which tells us the pressure is a little bit lower, and the reuse of pre-existing normal faults, producing quite steep angled reverse faults that push blocks of rock straight up. Now, the question becomes, why did the Farallon plate change its angle of subduction? So there's a couple of possible reasons which might explain why the Farallon plate essentially found it so difficult to subduct. The first possible reason is that attached to the Farallon plate there was a buoyant oceanic plateau. Now, most oceanic plateaus on the seafloor are the result of flood basalt eruption. So that's when you have a large fissure eruption on the seafloor, so huge amounts of basalt come pouring out onto the seafloor, and essentially it creates an area of raised terrain on the seafloor. And of course, as the name suggests, this area of raised terrain has a flat top, so we call it a plateau. Now, some ocean plateaus, on the other hand, can actually consist of continental crust. And as we know, continental crust is actually quite difficult to subduct. So if we have a very, very thick ocean plateau made of basalt, or some kind of oceanic plateau that's made of continental crust, well, when that oceanic plateau is being subducted, because remember it's sitting on top of the Farallon plate, it's going to be naturally buoyant. So it's going to naturally want to rise. Now, this is a bit of a problem because the Farallon plate wants to go down into the mantle. It wants to essentially wants to subduct, but this buoyant oceanic plateau is going to counteract that. So it's going to want to pull the subducting slab upwards. And so if you had a large enough oceanic plateau that was buoyant enough, it would be sufficient to pull the Farallon plate essentially into a shallower angle of subduction, and eventually leading it to subduct almost horizontally along the underside of the North American plate. So that's option number one. Our second option is that there is a mantle plume that gets stuck underneath the Farallon plate. So obviously to the west of the Farallon plate we have the Farallon spreading ridge, which is where new oceanic crust is being made. Now, a lot of the time when we have oceanic ridges, it's not uncommon for mantle plumes to get trapped under the spreading ridge. And this is because most spreading ridges are located at the interface between convection cells in the mantle. So you have two convection cells that are running parallel to each other, and the contact between the two of them is a very, very common location for spreading ridges to form, but it's also a good path along which rising mantle plumes will move. It's a path of least resistance. And so it's not uncommon for mantle plumes to get stuck underneath spreading ridges. The classic example of that is, of course, the mantle plume that's forming Iceland, which is a big mantle plume that's currently trapped under the Mid-Atlantic ridge in the North Atlantic. Now, in the case of the Farallon spreading ridge, we think there's a chance that the mantle plume might have been moving up to essentially rise underneath the Farallon spreading ridge. However, instead of going straight up and getting caught under the ridge, it in fact got deflected and it went to the east, and it got trapped under the oceanic crust of the Farallon plate. And so what this means is underneath the Farallon plate, you're going to have this big ball of very hot, very buoyant mafic magma. And so once again, this is going to have the effect of pushing up the Farallon plate, thereby making it far more difficult to subduct. And so obviously, because you've got this big buoyant mass of magma trapped underneath it, when it starts to try and subduct that piece of oceanic crust with the magma underneath it, it's not going to subduct easily. In fact, the magma is going to be so buoyant, it's just going to push up the Farallon plate, and once again, it's going to make the angle of subduction become near horizontal. Now, out of these two models, the mantle plume model is the preferred option. Now, obviously, as we've said, the shift in the angle of subduction leads to volcanism ceasing, because obviously if our piece of subducting oceanic crust is not making it down to 150 kilometers, it's not melting the mantle, so we're not producing magma. Now, as also discussed, because we have this eastward shift in deformation and this change in how strong the deformation is, we see a change from these tight folds and thrust faults, which we see with the Siever and Nevadian orogenies, and we see a change to what's called a larger scale crustal buckling, which produces big open anticlines and synclines, and obviously the previously mentioned steep reverse faults, which are pushing up these blocks of rock. So by the Middle Eocene, so that's the Paleogene period, the Laramide deformation had ceased and igneous activity had returned. So this is important. So this would suggest that something has changed. Now, the renewed activity is thought to have been due to the mantle plume under the subducting Farallon plate breaking through. And so this means the mantle plume can then get stuck underneath the continental crust, and then the magma will slowly work its way to the surface where it will be erupted via volcanoes. In terms of the magma that's being erupted from the volcanoes post-Laramide, we see the magma is mostly of a mafic composition. And this would be consistent with a mantle plume, because a mantle plume will typically produce mafic magmas, which result in the formation of basalt. So if you think of the islands of Iceland or the islands of Hawaii, these are island chains which are the result of mantle plume activity, and as I'm sure you know, they consist mostly of basalt lava flows. So here's our basic model. So the Farallon spreading ridge is going to be off somewhere to the left. That's the divergent boundary where new crust is being made. And normally a mantle plume would get stuck under the spreading ridge. However, in this model, we think the mantle plume may well have gotten deflected, and it gets trapped underneath the seafloor of the Farallon plate. So this is the oceanic crust of the Farallon plate, and underneath it we have our mantle plume. And once again, our mantle plume is, it's hot magma, it's buoyant magma, it wants to rise. And so when this portion of the oceanic crust is being subducted, instead of diving down into the mantle at a normal angle, the buoyancy of the mantle plume pushes the oceanic crust upwards and essentially makes it grind along the bottom of the North American plate. So essentially our angle of subduction is near horizontal. Now, this means that the deformation that we're seeing, instead of being focused over here towards the front of the subduction zone, it's now being spread out throughout this entire region. So this area here was affected by the Nevadian and the Seaver orogenies. This area back here is now being affected by the Laramide orogeny, because the deformation is being spread over this broader region. And so it's in this region we're going to see these big open folds, and we're going to see these steep reverse faults pushing up blocks of rock. And obviously, as I said, that's different to the type of deformation we see over here, which consists of tight folding and thrust faults. Now, eventually what's going to happen is the mantle plume is going to slowly burn its way through the oceanic crust of the Farallon plate. And so when that happens, obviously the Farallon plate is then going to be able to continue subducting normally. We're going to have fragments of the Farallon plate left behind, but what we're going to end up with, though, is the mantle plume now stuck underneath the continental lithosphere. That magma is going to slowly make its way to the surface, where it's going to be erupted via volcanoes. So it's at this point that we see the return of volcanism along the western margin of North America. And quite a lot of that volcanism is mafic in composition, which would be consistent with magmas which are being sourced from a mantle plume. Okay, so now let's think about the Pacific coastline as a whole. So before the Eocene, the entire length of the Pacific coast was a convergent plate boundary. So it was an ocean-continent convergent plate boundary. So we had a subduction zone. And of course, we know at this subduction zone, the Farallon plate was subducting underneath the North American plate. Now, at present, we actually have two fragments of the Farallon plate left, and they've been split into two separate plates. We have the Juan de Fuca plate, which is located off the coast of Oregon and Washington state primarily, and the Cocos plate, which is located off the western coast of Central America. Now, the westward movement of North America led to its collision with the Pacific Farallon Ridge during the Eocene. And so the Pacific Farallon Ridge essentially is the spreading ridge which is creating new oceanic crust for the Farallon plate. And we know that because North America is moving westwards, eventually it's going to roll over the top of the spreading ridge, and we know this happened approximately in the Eocene. Now, the Pacific Farallon Ridge is orientated approximately northeast-southwest. So this means that as North America was moving westwards, it didn't hit the Farallon Ridge at the same time, or should I say, didn't hit the full extent of the Farallon Ridge at the same time. Instead, it hit the top of the Farallon Ridge first, and as it kept moving westwards, more and more of the Farallon Ridge got subducted underneath North America. So if we look here, we can see our situation. So here's the Farallon Ridge. This is our divergent plate boundary at which new oceanic crust is being made, which forms part of the Farallon Plate. We can see the Farallon Plate is subducting underneath North America along a trench which is located approximately here. Now you'll notice that the Farallon Ridge is orientated approximately northeast southwest, and this means that as North America has been moving westwards, the first place it intersects with the Farallon Ridge is going to be up here in the north by Alaska. But then steadily as North America continues to move westwards over the Farallon Plate, it's going to steadily destroy more and more of the Farallon spreading ridge. Now, in terms of the Eocene to the Oligocene, so that's about 40 million years ago, we have the area around Alaska, around the Alaskan-Canadian border, intersects the Farallon Ridge. The North American Plate intersects more of the ridge, with the Gulf of California intersecting it by the Oligocene. So you'll notice just down here, we have this, essentially this transform fault here, which is separating these two segments of the spreading ridge. And so we know that initial contact is going to be made up here, but eventually as North America continues to move westwards, it's going to hit this portion of the ridge down here. So by intersecting the Farallon Ridge, the Cordilleran margin shifted from subduction to transform tectonics. So we see this change from being a fully active margin where we have a subduction zone running all the way down the western margin of North America to a situation where we have short active margins along the west coast of North America, but also two very, very large transform plate boundaries, the San Andreas plate boundary and the Queen Charlotte / Fairweather plate boundary. So here's our situation. So here we are 40 million years ago. Again, here's the Farallon spreading ridge, and North America's moving westward. So we know it initially intersects with the Farallon Ridge up here in Alaska, and then as North America continues to move westwards, it's eventually going to hit this portion of the Farallon Ridge right here. And that's exactly what happened. So here's 20 million years ago. So this portion up here of the Farallon spreading ridge has subducted underneath North America. This region down here has subducted underneath North America, and you can see we now have two segments of the Farallon Ridge left. So at this point we now have the remnant of the Farallon Plate here and the remnant of the Farallon Plate down here, and North America is going to continue moving westwards. So essentially this region here is going to get smaller and smaller, and you can see by the present day this is what's left of the Farallon spreading ridge. It's now the spreading ridge for the Juan de Fuca Plate, which is this little plate right here. And the oceanic crust here is subducting underneath North America along the Cascadia subduction zone, which stretches from northern California here to southern British Columbia here. You'll also notice that down here we now have the Cocos Plate, so this portion of the spreading ridge down here, which represents this area down there, essentially is forming the Cocos spreading ridge, which is producing new oceanic crust for the Cocos Plate, which is subducting underneath Central America. Now what this means is the Pacific Plate in general is moving in an approximately northwesterly direction, and so this means that the contact between the Pacific Plate here and the North American Plate here has to become a transform plate boundary, and of course this is the San Andreas transform fault. Now we also have the development of a transform plate boundary up here. So this is the Queen Charlotte fault if you're in Canada, or the Fairweather fault if you're in Alaska. So if we just zoom in on the Juan de Fuca Plate down here in the Cascadia subduction zone, sorry, I do apologize. You can see it here in this Google Earth image. You can see the trench quite clearly there. You can see that it's associated with a line of volcanoes running from southern British Columbia to northern California, and you can actually see that the plate itself is actually split into three separate small plates. So we have the Juan de Fuca Plate proper, then we have the Explorer Plate up here, and the Gorda Plate down here, and they're actually separated by these transform faults, which are located there and there. But on the whole, we typically refer to these three plates together simply as the Juan de Fuca Plate, just to keep things simple. So during the Miocene, the two triple junctions that form, so a triple junction is a place where three plates meet, and we developed two of them off the west coast of North America. So if we come back over here, here are our triple junctions. So we've got one right here where we have the Juan de Fuca plate meeting the Pacific plate meeting the North American plate. And we have another triple junction down here where we have the Cocos plate meeting the Pacific plate meeting the North American plate. So, as discussed, the westward movement of the North American plate over the Farallon plate essentially begins to push these two triple junctions apart, and it leads to the formation of our transform faults in order to accommodate the northwestward movement of North America. So we end up with the San Andreas transform fault, which runs along the coast of California, and the Queen Charlotte transform fault, which runs along the west coast of Canada, which of course becomes the Fairweather fault as you enter Alaska. So in terms of these faults, the San Andreas and the Queen Charlotte fault, these faults are right lateral strike-slip faults. So this means that the right block, which is continental North America, is effectively moving to the southeast, and the left-hand block, which is Baja California and a bit of the west coast plus the Pacific plate, is moving to the northwest. So if we just go back, we can see that the Pacific plate here, including Baja California and a bit of the Californian coast, is moving in a northwesterly direction, which therefore means that North America, must therefore be moving in a southeasterly direction, because they obviously have to move in opposite directions to each other. So we're now going to run through a few areas of interest when it comes to the development of North America during the Paleogene and the Neogene. So we're going to be looking at a few areas which are experiencing interesting tectonic processes during the Cenozoic. So the first of these regions is going to be the Rio Grande Rift. And if we look at the picture of the Rio Grande Rift here, you can see that essentially it's located in southern Colorado, cuts all the way through New Mexico, and then enters Texas along approximately the Texas-Mexican border. So the Rio Grande Rift is approximately 1,000 kilometers long, and as I said, it extends from Colorado all the way down into Texas and Mexico. So the rift is due to crustal extension. So this area here is being stretched, so the crust is being thinned, and this is leading to the formation of a rift valley. And it just so happens that because there's a pre-existing valley there, the Rio Grande River thought to itself, right, that's the easiest path to take, and so the Rio Grande River uses this Rio Grande Rift Valley because it's just there. So unlike most rifts, it's likely not due to mantle plume activity. So a lot of the time when we see rifts forming, it's typically because the crust is being stretched due to the presence of a large body of magma trapped underneath the rift valley. But we don't really see that with the Rio Grande Rift. Normally when we see that, we see lots and lots of magma pouring to the surface via fissure eruptions, and we see the area being covered in lots and lots of flood basalts, but we don't have that happening here. To be clear, we do have volcanism along the Rio Grande Rift, but it's not that big. So rifting in the Rio Grande area began approximately 30 million years ago, so it's post-Laramidogene, and rifting begins during a period of volcanic activity. So post-Laramide, as mentioned, we have the reoccurrence of volcanism along the western margin of North America, and it's possible that this volcanism may have helped to have weakened the continental lithosphere because there's so much magma passing through it. It essentially breaks up the continental crust, meaning it's not a solid cohesive unit anymore. It's far more flexible, and this might have allowed the rifting to begin, or at least might have encouraged it, made it easier. Now we know that under the rift the lithosphere has deformed, and this deformation has allowed the asthenosphere to upwell. So it's allowed the asthenosphere to rise into the continental lithosphere. So here we go. So this diagram here is a simplified diagram of what we see for the Rio Grande Valley. So this grey area here is essentially the continental crust, and beneath it in this kind of browny yellow orange color we have the lithospheric mantle. So the crust plus this bit of mantle here combined is the continental lithosphere. Now what we see under the Rio Grande Valley is the crust has thinned, and this thinning has allowed the asthenosphere to rise up into the depression that it creates. And obviously we know the asthenosphere is a semi-solid layer, so it's a mixture of both magma and solid crystals. And so the heat from the asthenosphere and also the magma present in the asthenosphere helps to feed magma into the crust, which leads to the formation of intrusions in the crust and also limited volcanism at the surface. Now, we know that the asthenosphere must have risen up here because when we look at the geophysics for the area, we see the following. So this diagram here is showing you seismic wave velocities. Now, typically, when a seismic wave passes through a liquid layer, like the asthenosphere, it slows down. So the more liquid your layer is, the more plastic and flexible it is, the slower your seismic waves will move. The more solid your layer is, the quicker the seismic waves will move. And so what we notice is that underneath the Rio Grande Rift, we have this orange area here, and that's showing us lower seismic velocities than the regions either side, which are here in blues and greens. So this is showing us that underneath the Rio Grande Valley, we obviously have this region where we have essentially a large amount of liquid or semi-liquid rock. And this is going to be the asthenosphere upwelling into the base of the continental lithosphere. And as discussed, essentially, this upwelling of the asthenosphere leads to the formation of magmas, which are seen at the surface as volcanoes. So the cause of the rifting for the Rio Grande Valley is actually a little bit uncertain. So there's three possible causes for it. The first possible cause is the Colorado Plateau. Now, some models suggest that the Colorado Plateau, which is located to the west of the Rio Grande Rift, is actually acting as its own little microcontinent. So it's acting as its own independent block, essentially. And we think that the Colorado Plateau is actually rotating clockwise, and we think it might have rotated about 1 to 1.5 degrees. Now, this rotation essentially will have caused the continental crust to become stretched. So essentially, it's going to have to extend as the Colorado Plateau rotates. And so this could possibly lead to the crust around the Rio Grande region becoming extended, and this could possibly explain why rifting begins. There's also the possibility that it could have been driven by some kind of mantle upwelling, and this mantle upwelling could have been driven by mantle convection or delamination. Delamination is when the bottom part of the crust falls off. So if I just go back here, here's our diagram. So if you imagine, in the case of delamination, a portion of this lithospheric mantle here could detach from the base of the continental crust. And so the lithospheric mantle drops off, and this allows the asthenosphere to rise up into the place where it had been. And so that's a case of delamination. The other possibility is that there's just a couple of mantle convection cells under the Rio Grande Rift here, and the mantle convection essentially is just trying to pull this bit of the continental crust to the east, this bit of the continental crust to the west, and so it's causing the area of the Rio Grande Rift to become extended. The final option is that the onset of rifting in the Rio Grande area is a result of transform faulting. So it's caused by the development of the San Andreas Fault. And so, as we've discussed, the San Andreas Fault is a right lateral strike slip fault. So North America is essentially trying to move to the southeast. The Pacific plate is trying to move to the northwest. And so this movement of one plate past another could, in theory, produce the right conditions that could lead to the area around the Rio Grande entering extension. Now, we know that the extension in the Rio Grande area has occurred in 3 pulses, and the most recent of these pulses occurred in the Pliocene. So that's about 5 million years ago. And the rifting that we see in the Rio Grande Valley is still active now. Now, it's only happening at a rate of about 1.5 to 2.5 millimeters a year. So it's actually very, very slow, but it is occurring. Just to give you some idea for comparison, by the way, the Mid-Atlantic ridge in the middle of the Atlantic is spreading at a rate of about 2.5 centimeters a year. And so this diagram here is just going to show you. So here's the diagram we saw earlier showing you the Rio Grande Rift. Now, these arrows are pointing to several key towns along the length of the Rio Grande Rift, just so we can essentially match up our locations there on this map. And what you'll notice is that the Rio Grande Rift is associated with all of this red material here, which are volcanic rocks which are less than 5 million years in age. So this is young volcanism associated with the rifting event. And you can actually see down here, so here we go, so this actually shows you, this is the Petrillo volcanic field. It's located down here at the bottom, and you can quite clearly see the volcanoes there visible on the surface as the black spots. And the fact these volcanoes have this very black color indicates to us that the magma is going to be of a more mafic composition. So these are going to be basaltic volcanoes, and once again that's consistent with rifting, because rifting is going to induce mantle melting, which is going to lead to the formation of mafic magmas, which when they cool can form rocks like basalt. Okay, so let's stop part 2 here. So get up, have a walk around, get a glass of water, take 5 or 10 minutes to relax, and then please come back for part 3.